Okay, so we're going to continue looking at graphical interpretations of kinematics. I thought about going in and having examples of the position versus time graph or the acceleration versus time graph, but for those, you can really only, for position versus time, you look at the slope and you get towards the velocity, and then for the acceleration, you use the area under the curve to get back to the velocity. So I kind of get the most function out of taking a look at the velocity. For the most part, you would end up with just the same thing on a position versus time graph. You would only look at the slope and then you could get to the velocity. So you would just do what we saw in the other video where you're applying the slopes to deal with that. And then with the acceleration, you would only look at the area under the curve. It's basically doing the exact same thing that we're doing here with the velocity versus time graph. You just have a different looking graph that you're putting it into. Okay? Most of the ones that you do this on, unless you're using calculus, you have nice sharp edges. For instance, the velocity versus time graph that we're dealing with is not something that's fully physical because this is non-differentiable at these sharp edges here when we go from one to another. But this is the type of graph that is usually given when we're dealing with that sort of thing. Now this is a slightly different velocity versus time graph. I wanted to take a look at this one because it includes something that you may run into and it's something worth keeping track of. We've got a situation where now here's our, actually let me use black on that. Here is our 0 point. This is 0 meters per second. Let's scoot that back. Okay, and so now I've got a situation where down here this is -1, this is -2, -3, this is 1, 2, 3. We have a situation where our velocity actually goes down into the negative values, which means it's a velocity in the opposite direction. Okay? That has an effect on our displacement, how we're going to look at that. And so I wanted to have something that incorporated that as well. Now you'll notice we've got a positive velocity, we've got a slope here where we start from 0. We have a positive slope because we're going up, and that means a positive acceleration, so we go up to 1 meter per second in the positive direction. We end up with a flat line, so that's a 0 slope, and that goes on for a while. So we're not accelerating, but we're traveling along at a velocity of 1 meter per second. We have another acceleration where we go up all the way up to 2 meters per second, and then we end up going down. We have a pretty sharp slope there. It's a negative slope, so we have an acceleration in the opposite direction. And you'll see that it doesn't stop when we hit 0. It continues accelerating us in the negative direction, giving us a velocity going in the negative direction. So we're starting to go, that's basically us moving forward. We stop, and then we start moving backwards. Okay? So the displacement that we actually find, so for instance, if I want to look for my displacement from, let's go t equals 6 to t equals 8, I would find the area under the curve, and this is where it's a little bit different. Okay? So in this case, I'm not looking for the area down here because that could go on down to -infinity. What we mean by the area under the curve is actually the area in between our line and our x-axis. Basically, whatever our y values are, wherever that guy is 0, that's where we're getting the area with respect to. So in this case, I have once again a triangle here, and I have a situation where my area is going to be, so we'll call this guy area 1, and this guy area 2, just like we did before. I know my total area is the combination of those two. Let me get some more room here. And so A1 is going to be equal to 1/2 base times height, because it's a triangle. Well, my base is going to be 6 to 7 seconds, so that's 1/2 1 second, from 6 to 7 seconds. And then my height, well, I could keep track of the negative in here, and so that's one way of doing it. My height is from 0 down to -2 meters per second. So go ahead and use the actual values on the graph, and it will actually carry your negatives through for you. And we'll find, just like we saw in the past, divided by seconds cancels out with our seconds, and we're left with, so my 2 cancels out there, we end up with -1 meter. Okay? Area 2, well, that guy's a rectangle, so we just want base times height, and that's going to be equal to my base is, once again, 1 second, and my height is negative 2 meters per second. That's how, from here, this is negative 2 meters per second, up to there. So if I include the negative in there, then I can keep track of it just in the equations. And so I'll multiply this through, and I end up with negative 2 meters. So my total displacement area, my total area, is area 1 plus area 2, which is going to be equal to minus 1 plus a minus 2 meters, gives me minus 3 meters. That's my total displacement. Now, if you don't pay close attention to the negative sign here, and you just treat the height as, oh, well, this is 2 meters per second tall, right? And so 1, 2, you just treat it as though it's a positive. Then you can do that, but you want to keep in mind that right now, my velocity is negative, right? So I'm going the opposite direction. So the total area that I get here should be a negative displacement. I'm displacing, I'm going in the opposite direction. Now, if we've got a situation where it's basically, if we've got an area that's symmetric, so if I look at this, let's clear that up some. If I've got a situation where I want to look from here to here, I can see that this goes from 2 meters per second down to negative 2 meters per second. And my middle point is 6 seconds. Basically, it's in the middle. So this is 5 seconds, this is 6 seconds, and this is 7 seconds. I've got a situation where I've got the area of this guy versus the area of this guy. I didn't draw my lines as well as I could have. I apologize. But we've got this triangle, which is going to be 2 meters per second tall and 1 second wide for my base. This is 1 second wide and negative 2 meters per second tall. When I add those two areas together, I'll end up with a total displacement equal to 0 meters. Give that a try. See what you come up with. So I go from 5 seconds and a height of 2 meters per second all the way over to 7 seconds and negative 2 meters per second with a straight line the whole time. Basically what happens is I'm moving along, I come to a stop, and then I back up, and then that's when time runs out. So I end up pretty much right back where I started. And we can see that because I've got just as much area above the graph as I do below, so they cancel each other out. I could broaden this out and find out the total displacement for the entire time just by finding the area here and subtracting off the area, let's go with a different color, down here. And if I go all the way to the end, then I would go over to here where my graph ends. This is the total positive displacement that I have, my total negative displacement when I'm going the opposite direction. And so by finding all those areas and adding them up, I'd be able to find what my total displacement is over this entire period. Okay? So again, this is using graphs to understand kinematic values. And the key to it is this little chart guy here. It's always a position versus time graph, or a velocity versus time, or an acceleration versus time. We always have a situation where our graph is whatever value in question is my y-axis, and then it's versus time in the x. And if I look at the slopes, I can go from my position, my x versus t, to find my velocities. Or if I've got velocity, I can find my acceleration. Right? And then area under the curve lets me go back the other way. So